According to the National Electrical Code, for typical power panels, a grounded conductor is not required to be installed with a feeder supplying power to a three-phase panel that doesn't need the grounded conductor for any of the branch circuits. An equipment grounding conductor, however, is required to be installed to carry fault current back to the source. It sounds like the electrician may be referring to a 3-wire delta system consisting of line 1, line 2, and line 3. This type of system does not inherently require a neutral conductor. However, a 4th wire is indeed often required for grounding the transformer, especially in what's known as a high-leg delta system. In a high-leg delta configuration, each leg has 120 volts to ground, but there exists 208 volts between any two legs. American 3-phase delta transformer secondary wiring typically mandates the 4th wire to ground the transformer, primarily to ensure safety. It's important to distinguish that this 4th wire is not a neutral conductor in this scenario, but rather an equipment grounding conductor. In a 4-wire delta system, the equipment grounding conductor is connected to the neutral point of the transformer's secondary winding. This neutral point is typically the center tap of the winding. This connection provides a crucial path for fault current to return to the source, facilitating the operation of overcurrent protective devices and minimizing potential hazards. Furthermore, it establishes a stable reference point for the system's voltage. In a standard 3-phase system, the equipment grounding conductor serves another vital purpose. It connects the neutral point of the transformer, when present, to the grounding electrode system of the building. This connection creates a low impedance path for fault current to flow back to the source, enhancing the effectiveness of protective devices. Moreover, it plays a significant role in protecting against electrical shock by maintaining a stable ground reference and limiting voltage potential between conductive surfaces and ground. To further elaborate on grounding and bonding, let's delve into some key concepts and requirements outlined in the National Electrical Code, or NEC. Firstly, grounding refers to connecting electrical circuits and equipment to the earth, providing a path for fault current to flow back to the source, thus facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. Secondly, bonding, on the other hand, involves connecting non-current carrying metal parts of electrical equipment together to create a low impedance path for fault current. The purpose is to minimize voltage potential between these metal parts and ground, thereby reducing the risk of electrical shock. Now let's explore the different types of grounding systems commonly used in electrical installations. 1. The grounded system, also known as the neutral grounded system, has one of the current carrying conductors intentionally connected to ground. This is the most common type of grounding system used in residential and commercial buildings. 2. The ungrounded system, in contrast, does not have any of the current carrying conductors intentionally connected to ground. While less common, it's sometimes used in industrial applications where a high degree of service continuity is required. 3. The impedance grounded system uses an impedance such as a resistor to limit the amount of fault current that can flow to ground. This type of system is often used in industrial facilities with large electrical loads. Moving on to the equipment grounding conductor, or EG, this is a critical component of the grounding system. It provides a low impedance path for fault current to flow back to the source from non-current carrying metal parts of electrical equipment. The EGC can be a wire, a metal raceway, or other approved conductor. The size of the EGC is determined by the size of the overcurrent protective device protecting the circuit. In addition to the EGC, there is also the grounding electrode conductor, or GEC. This conductor connects the grounding electrode system to the electrical system. The grounding electrode system typically consists of one or more grounding electrodes such as ground rods, ground plates, or metal water pipes. The size of the GEC is determined by the size of the service entrance conductors. The NEC provides detailed requirements for grounding and bonding in Article 250. This article covers everything from the types of grounding systems permitted to the sizing of grounding conductors and the installation of grounding electrodes. It's crucial for electricians and electrical contractors to have a thorough understanding of Article 250 to ensure safe and compliant electrical installations. Now let's address some common misconceptions about grounding and bonding. 1. Grounding guarantees complete protection against electrical shock. While grounding significantly reduces the risk of electrical shock, it doesn't eliminate it entirely. Other safety measures, such as using ground fault circuit interrupters, or GFCIs, and following safe work practices are also essential. 2. Any metal object buried in the ground can serve as a grounding electrode. Only approved grounding electrodes, such as ground rods, ground plates, and metal water pipes, can be used as grounding electrodes. Other metal objects may not provide a reliable connection to ground and could be hazardous. 3. Bonding is only necessary in wet locations. Bonding is required in all locations, not just wet locations. Bonding helps to minimize voltage potential between non-current carrying metal parts of electrical equipment, regardless of the environment. Now let's consider some practical applications of grounding and bonding. 1. In a residential wiring system, the grounding system typically consists of a ground rod driven into the earth and connected to the service panel with a grounding electrode conductor. The equipment grounding conductors and branch circuits connect to the grounding bus in the service panel, providing a path for fault current to flow back to the source. 2. In a commercial building, the grounding system may include multiple grounding electrodes, such as ground rods and metal water pipes, interconnected to form a grounding electrode system. The equipment grounding conductors connect to the grounding bus in each panel board, providing a low impedance path for fault current. 3. In an industrial facility, the grounding system may be more complex, involving impedance grounding and specially designed grounding electrodes to handle large fault currents. Regular inspection and testing of grounding and bonding systems are essential to ensure their effectiveness. Ground resistance testing can verify the integrity of the grounding electrode system, while continuity testing can verify the integrity of bonding connections. Any deficiencies identified during inspection and testing should be promptly corrected to maintain a safe electrical system. Furthermore, it's important to consider the impact of sensitive electronic equipment on grounding and bonding requirements. Sensitive electronic equipment, such as computers and medical devices, may require a dedicated grounding system to minimize electrical noise and prevent malfunctions. The NEC provides specific requirements for grounding sensitive electronic equipment in Article 647. Let's delve deeper into the nuances of three-phase power systems and the role of the grounded conductor. In a three-phase system, power is delivered using three alternating current waveforms that are offset by 120 electrical degrees. This configuration offers several advantages over single-phase systems, including high power capacity, smoother power delivery, and improved motor performance. There are two primary types of three-phase systems: 1, the Y system, and 2, the Delta system. In a Y system, the three phases are connected in a Y configuration with a neutral point at the center of the Y. The voltage between each phase and the neutral point is called the phase voltage, while the voltage between any two phases is called the line voltage. In a Delta system, the three phases are connected in a closed loop, forming a triangle or delta shape. There is no neutral point in a standard Delta system. The voltage between any two phases is the line voltage. Now let's consider the role of the grounded conductor, also known as the neutral conductor, in a three-phase system. In a Y system, the neutral conductor is typically grounded, providing a reference point for the system voltage and a path for fault current to flow back to the source. The grounded conductor also helps to stabilize the voltage on each phase, minimizing voltage imbalances. In a Delta system, the grounded conductor may or may not be present depending on the specific configuration and application. In a corner-grounded Delta system, one of the phase conductors is grounded. This configuration provides a simple and cost-effective way to establish a ground reference. In a center-tapped Delta system, a center tap on one of the phase windings is grounded. This configuration provides a neutral point that can be used to supply single-phase loads. However, it's important to note that the voltage between one of the phase conductors and the neutral point will be higher than the voltage between the other two phase conductors and the neutral point. This is commonly referred to as the high leg or wild leg. When working with three-phase systems, it's crucial to understand the voltage relationships between the phases and the neutral point. Incorrectly connecting loads to the wrong voltage can result in equipment damage or even electrical shock. Therefore, it's essential to use appropriate measuring instruments and follow safe work practices when installing and maintaining three-phase systems. In summary, the presence of a grounded conductor in a three-phase system depends on the specific configuration and application. While a grounded conductor is typically required in Y systems to provide a reference point and a path for fault current, it may or may not be present in Delta systems, depending on the grounding scheme. Regardless of the grounding configuration, it's essential to ensure that all electrical work is performed by qualified personnel in accordance with applicable codes and standards. Furthermore, it's crucial to properly size and install equipment grounding conductors to provide a low impedance path for fault current and minimize the risk of electrical shock. Regularly inspecting and testing grounding systems can help identify and correct any deficiencies, ensuring a safe and reliable electrical system.